Part 2 of Unit 2 is focused on normal distributions. Going from what we learned about relative frequency histograms in Unit 2, page 20, and in particular we're going to focus on random variables that are continuous. Okay, so for continuous random variable, this is the relative frequency histogram. And what I'm going to say now is if I had all of the possible observations, so imagine if I had taken a census to collect a sample for the variable I'm interested in, the variable x represented by uppercase X. So this could be, for instance, you're going to see I focus on the variable women's heights, adult women heights, so women over 18. So this is a continuous random variable because you can have fractions of a height or decimal value in measuring the height, depending on how precise your measurement tool is. So what we can do then is imagine having an entire census done on the variable. So if I was to have a census, what do I think the distribution would look like? So I believe that the distribution of all of the possible observations would look similar to the histogram. It's just a smoothed out version, an idealized version of the relative frequency histogram. In doing this, what I'm saying is I believe that if I collected more data, I would have the possibility of more precision. Because I have more precision, I can take an interval for my rectangles or my bars in the relative frequency histogram. I can take intervals that are much smaller than before. So because I can have much narrower intervals, see what happens is imagine narrower and narrower intervals making narrower and narrower bars. So there's just a couple to show you what I intend to versus what we had before. This is the kind of, oops. So notice if I try and smooth out this bar, it leaves this gap here, this set of bars, but if I smooth out this set of bars, it has much smaller gap. So what I'm saying when I smooth out a relative frequency histogram, as I did here, is that I'm saying that I could have more precision like here, and essentially I'm smoothing out, because I'm making thinner and thinner intervals, I'm smoothing out the relative frequency histogram. Alright. So this smoothed out version of the relative frequency histogram is called a density curve. Okay, and each density curve, whatever density curve, has certain properties. Properties of density curve, there's 4 of them. And they get their properties from the relative frequency histogram. One is that the area under the density curve is 100%. Remember, that's what the bars will total to, 100%. So that's convenient. You'll see why. Another important point is because this is a continuous distribution for a continuous variable, we calculate density. So now we're going to talk about the density between values for the variable and not at a particular variable. Let me describe to you what I mean. I want to make an additional point before I show you that. Here's the density curve that represents the idealized version if we were to have all the values, all possible values for the variable x. Then since it's symmetric, then we can say that the mean is equal to the median is equal to the mode. It's right in the center, and we're going to use the symbol Mu, remember, because this is the symbol we use when we are referring to the population mean. Okay, so this center represents the population mean. And along here are the values that it takes, that the variable x, big X, takes on. Because it's going to be the values we need to differentiate, we're going to use little x to represent any specific value. So let's say we were to speak of women's heights, and I used my examples, I prepared my examples in inches. So let's say the mean is at 64. So the population mean would be 64, and that would be right in the center, let's say. And I'm going to divide the density curve in half exactly. Well, if we divide the density curve in half, then what is half of the density curve? What is the area under half of it? So we could write that actually as P, that the curve, under the curve, less than little x of 64 is equal. The P represents proportion of observations, so P for proportion. It's also the percentage of observations. And because we are talking about the idealized version of the relative frequency histogram, because we have considered everyone, any mention of proportion is actually talking about probability of seeing a certain outcome. Okay? So we can call this also probability. So these terms are interchangeable. In problem solving, you'll be asked questions like these. What's the proportion of observations under the curve, that's represented by big X, that are less than 64 inches in this case? Well, the whole thing is 100, so half would be 50%. So we could write that either as 50% or in decimal form as 0.5. Another question I can ask is to find the proportion of observations between two bars. So let's say I wanted you to go between 64 and, say this was 60. What are the proportion of observations in these bars or under the curve, the density curve? I would write that as the P, that X is between 60 and 64, and we'd have to find it out. So we could answer that question. Let's say it turned out to be, let's say this to the left of this is 50%, and let's say it's the case that to the left of this is 25%. So how would we figure out the shaded region? Well, 50 take away 25 leaves 25%. So the answer is 25% of the observations, or 0.25. So this is how we analyze what to expect. Okay, this is the goal of statistics, to characterize a variable and make predictions after you've done so. So this can be interpreted as the probability that a woman chosen at random would have a height between 60 and 64 inches. The chance is 25%. if these were actually the case. So I give you these numbers. Now, back to point number 2. What about the area or the density under the curve at a particular value? What if someone asked you what was the probability or proportion of observations such that x is equal to exactly 64? Well, the fact is that when we talk about a continuous variable, we only interpret density between values, okay, in this case between 60 and 64, in this case x being less than 64 is 50%, so it's a range of values. But at our particular value, the answer is 0. This is supposed to be an equal sign. Must equal exactly 0. Why and how did I get that? Well, there are infinitely many possibilities, we say. The chance that an observation takes on a particular value is so small that its chance we see as 0. That's just another way to think about it. Alternately, you can just remember that for continuous variables, density is only computed between a range of values and not a particular value. If you were to consider a continuous number line, let's say at 64, here we are, keep in mind this is continuous, so how many observations would there be between 64 and the next value? Well, what is the next value? Is it 65? Well, no, it's a continuous number line, so it doesn't have to be 65. It could be 64.5. Well, no, it can even be finer. What about 64.05? Well, even smaller. So the point I'm trying to make is that the space between, if I'm going to talk about 64 and I'm going to try and draw a line or say find the area right here, right beside 64, there's infinitely many values. Even if I went as close as here, the very act of drawing this line implicates or involves the values beside 64, and there's so many and they're so tight, it's hard to speak of exactly 64. You're really narrowing what you're looking at on this line. Like, this line's too thick. I'm touching 64.00001, and on the other side 63.99999. Okay, so it's very hard to draw a line and say what's the density of just that line. It's actually, there's nothing there. It's impossible. In other words, it's impossible to draw a line right at 64. So we say the density is 0. Okay, so I gave you like 3 explanations. You never have to explain why to me again, but you need to remember that for a continuous random variable, the probability or the proportion or the percentage of observations exactly at x equals 64 is 0. The third point about density curves is that the pth percentile is defined such that p% of the area under the density curve lies to the left of it, including itself. So, just like we've been doing here, we would call 60 the 25th percentile because 60 is where, to the left of it, 25% of the observations reside. So we could write that 60, because of this, I'll write it in blue, 60 is known as the 25th percentile. Okay? And 64 is what? 64, because to the left of 64 is a 50% density, so 64 is the 50th percentile. Okay, so it's the median as well as the mean as well as the 50th percentile. So many ways to say the same thing. So let's try a few more examples to make sure you understand this concept. I'm not going to put a number here, but I'm going to say I know that X star has 10% of the observations to the left of it. How do I write that? And what is X star? X star is known as the 10th percentile because 10% of the observations are to the left of it. We would write probability of big X being smaller than little x star is equal to 10%. Okay, so this has to be going left. Okay, that's a percentile. Again, we could also write this as 10%. I'm fine with that. So if x star was 58, for instance, okay, then 58 would be the 10th percentile. We would write P of x less than 58 is 10%. All right, so I'm just saying if this was 10%, 58, put a value on it. What if I know 10% of the observations are up here? What would I call this value? Let's put a number on it. Let's call it 60 or 70. Let's call it 70. So that's 70. What do we call 70? Remember, a percentile is the value such that P% of the area is to the left of it. Left of it. So when we're looking here, we see 10% on the right. So how much is on the left? Well, if 10% is on the right, and there's 100% total under the curve, then it must be 90% on the left. And so we write it like this. And then in statistical notation, we write the chance or probability or proportion or percentage of observations less than 70 is equal to 90%. Notice I turned the direction to the left so I could talk about percentiles. And we would call 70 the 90th percentile. But just as it's 70 is sitting and straddling these two perspectives, another thing we could say is that 70 is in the top 10 percentile, which is important. You know, we like to know who's in the top 10 percentile, which people or which scores or which, you know, it's very interesting to know who's in the extreme. So we would also say 70, we could refer to 70 as being in the top 10 percentile. In case you were wondering, the symbol here means greater than, and the symbol to the left means less than. Okay, if you had doubt, just to clear that up, I've put that there. All right, a fourth point about density curves. Because density curves are idealized, we imagine that we have all information possible on the variable when we are smoothing out the underlying relative frequency histogram. When density curves are symmetric, we have a special name for the center or the mean of the distribution, as I explained. The mu is the Greek symbol for m, and we also have a special name for the spread, or the standard deviation. Sigma is the Greek letter for s, lowercase s in Greek. So we can apply to the density curve, as I mentioned before, at the center, since it's symmetric, well, the one that we're looking at is symmetric, we will refer to the center as mu.